Hello, and welcome to another one of my videos on the topic of management science, where we utilize Microsoft Excel to set up and then solve simple everyday business problems. Now, my two usual reminders before we get going. Number one, if you are watching this video on YouTube, please refer to the description below the video, and there you will find a link to the corresponding blog post for this problem. Now, on my blog, you will find the problem written out in long form with full tables, and most importantly, you will find a downloadable version of the very spreadsheet I'm going to use in this video. So you can go ahead and download it and follow right along step by step. And number two, about that spreadsheet, to make the video length reasonable, I've gone ahead and filled in certain features of the spreadsheet. Most notably, what I've done is I've gone ahead and named certain cell regions in the spreadsheet. And when we get to the spreadsheet part of the video, I'll show you exactly what that looks like. So let's go ahead and dive right in. Our problem for this video is called California Dreaming. And basically, they're a manufacturing company located out west, and they are considering some expansion in the California market. And we're going to help them decide whether or not they should build their factories and whether or not they should build a corresponding warehouse to go with the factory. Now, for any viewers that are not familiar with the layout of California, we're going to be dealing with the cities of San Francisco, which is in the top left of the map here, and then Los Angeles, which is down in the lower right. So our company is thinking about putting a factory in one or both cities, and if they build a factory in that city, they may put a warehouse as well. So we're going to help them decide what the best scenario is. So here's our problem summary. California Dreaming is considering an expansion to either Los Angeles, LA, or San Francisco. Now here are some criteria we have to keep in mind. They are willing to build a factory at either or both locations. They're also willing to build one warehouse, but only if a factory is built at the same location. So there will never be a warehouse without an accompanying factory. Now, it's also important to note here that they're only going to build one warehouse. So we will not have a situation where we have two factories and two warehouses. That is not an option. At most, they're willing to build one warehouse regardless of how many factories are built. Now, of course, each potential factory and or warehouse has certain capital requirements. It's going to take a certain amount of capital or money to build them. Each potential factory and or warehouse has a positive net present value, or NPV. I am not going to go into the finance behind all that. Suffice it to say that if the NPV is positive, that's a good thing, and we're just assuming that they're happy with the NPV in this project, so we'll just go on from there. Now, overall, the company is only willing to commit $10 million to this entire project. So we are constrained to a budget, a capital budget, of $10 million. And here is our total problem data summarized in a nice, neat table. Now, on the left, you will see the project. Should we build a factory in LA? Should we build a factory in San Francisco? Should we build a warehouse in LA? And should we build a warehouse in San Francisco? Now I'm going to skip over to the right-hand column where it says capital required. And again, that is the amount of capital required to build each project. So the LA factory would require $6 million. The San Francisco factory, $3 million. The LA warehouse would require $5 million. And the San Francisco warehouse, $2 million. Now, remember I said we're never going to have two factories and two warehouses. Well, one, we would not have that because of the constraint in the problem. But two, we would never have that because the cost would be too high. So having two factories and two warehouses would far exceed our budget over there. That would be $16 million, which is much more than 10. So just as a budgetary rule, we could never have that. Now, down the middle, we have our net present value. The company is happy with that, it's positive, and that's all we really need to know. Now, what we're trying to do here is we're going to try to come up with the right or the optimal combinations of projects that are going to maximize that net present value. So we're going to figure out which projects, which combination of factories and or warehouses, if there's a factory, will create the highest net present value while working within our constraint of $10 million total as far as the capital we have to work with. Now let's go ahead and go into Excel, and I will explain how the spreadsheet is set up, and then we'll go ahead and use the Excel solver to solve for our optimal solution. Okay, so here we are in Excel. Now I do want to remind you about one thing I said at the beginning of this video. To make the video length reasonable, I've gone ahead and built certain features into our blank spreadsheet, and they are in the one that hopefully you've downloaded and are now following along with. The most important feature I've built into the spreadsheet is the naming of cell regions. So I've gone in, selected certain areas of cells, and used the define name feature in Excel to give that region of cells a specific name. And here's what I mean by that. If I go up to our first set of tan colored cells under NPV, if I highlight those 6 cells and then we look up on the top left of our spreadsheet, you will see it says NPV. Likewise, if I go down below that to capital required and now look up at the top left, it says capital required. Now there are several of those in this spreadsheet. So when I use formulas here in a bit and I actually type in one of these named regions, I just want you to know, where they came from. So our first task will be a tour around the spreadsheet so we can just figure out what each part of it is going to do for us. Now on the top of our spreadsheet, where we have NPV, warehouse and factory, that is just the anticipated or the calculated net present value of each project. So for a warehouse in LA it was $6 million, a warehouse in San Francisco $4 million, etc. Now below that we have the capital required for each project. So a factory in LA is $6 million, a factory in San Francisco is $3 million, and so forth. Now over on the far right we have capital available. And if you remember, the total capital we have available in this project is $10 million. We cannot exceed a total project cost of $10 million. So that is going to be a constraint in our problem. Now below that, we have maximum warehouses. Remember that California Dreaming is only going to build a maximum of 1 warehouse. So even if we have factories in both cities, they're only going to be willing to build 1 warehouse. So we are setting the maximum number of warehouses in our problem to 1. Now let's go ahead and go to the purple cells to the left. Capital spent, once our problem has a solution, that will tell us how much of our $10 million we actually spent. So that will be determined by Excel's solution and the capital required costs there to the left. Total warehouses below that is simply the count of how many warehouses we're building. So it will either be 0 if we don't build any, or 1 if we build 1 in one city or the other. So that's simply a check on our constraint of maximum warehouses. To the left of that, we have build warehouse, and this is one of the cell regions Excel is going to find for us. And below that, we have build factory, and that's also a cell region Excel is going to find for us. Now I do want to point out, while we're down here in the solution area, that these problems are a specific type of problem. And basically they are a binary decision problem. So where it says build warehouse or build factory, Excel is either going to put a 0 in that cell or a 1. A 0 means do not build, a 1 means build. So in those light blue cells below LA and San Francisco and next to build warehouse and factory, we will have either 0 or a 1 in each cell. Now at the very bottom, we have total NPV, which is our total net present value in millions. And remember, we are trying to maximize that net present value through a certain combination of factories and warehouses. So that is what each region of our spreadsheet is going to do. So let's go ahead and start setting up formulas, which aren't very numerous, only a couple. and a few other things so we can go ahead and solve our problem. Okay, so let's go ahead and enter our three formulas. Then we'll go ahead and open up our solver and find our solution. So the first formula we're going to enter is going to be in the capital spent cell, which is the purple cell below capital spent. And that's just remind ourselves what this is going to tell us. Depending on the solution Excel finds in the build warehouse or build factory cells in the light blue at bottom, this will tell us how much of our capital of the $10 million we've actually spent. So this cell is a function of whether or not we've built a warehouse or factory, and then how much capital each corresponding project required. So we're going to use a formula here called sum product, and it looks like this. Equals sum product, and Excel can figure out what we want. Now we need to multiply whether or not we've built a warehouse or factory with the capital required. So this sum product function multiplies two cell arrays together, and then multiplies two things plus the next two things plus the next two things, etc. So we are multiplying two cell regions together of the same size, and that is capital required. So capital required, and actually there's a little drop down box that we can click, comma, and then of course whether or not we built anything. So we named that build with a question mark. All right, and then the next formula will just be a simple sum. Now remember, the maximum number of warehouses we can have is 1. So whatever is in total warehouses is going to be a sum of the two cells to the left of it. So we will either have no warehouses, or 1 in LA, 0 in San Francisco, or 0 in LA and 1 San Francisco. So those had better sum up to either 0 or 1. So we're just going to say sum build warehouse, and then close parentheses, and that's it. So basically that is just the sum of the two blue cells to the left of total warehouses. And believe it or not, we only have one more, and that is our total NPV at the bottom. So what will this formula be a function of? Well, total NPV is obviously going to have something to do with the NPV at the top, and of course it will. So it will have to do with the cell region at the very top of our spreadsheet, and it will have to do with whether or not we built it or not. So this will be another sum product function, but this time we're going to use the NPV cells at the top and then the build cells there at the very bottom. So this formula will be equals sum product. And then we want the NPV cells, so that will be NPV, comma, build, close parentheses. And you can see in the spreadsheet, Excel outlines each region. So the NPV region's in a thin blue line, and then the build warehouse region is in that thin green line. That tells you exactly what you just entered into your formula. So let's just double check those three. We'll go to capital spent. So sum product, capital required, build, looks good. And then total warehouses, we have sum of build warehouse, looks good there. And then in total NPV, we have the sum product of our NPV region at the top, and we're multiplying that with the build region, which is the two light blue rows there at the bottom. Everything looks good there. Okay, so our next step is to open up our solver, tell it what to look for, and then we'll have our solution. Okay, when we use the solver, I'm going to do it the really quick way. Then I'll open it back up and sort of show you what I've done. So let's go ahead and open up the solver. So we go to Data, and then Solver. Now, if you watch my other videos, you know pretty much how this works, or if you've used the solver in the past, you know how it works. So I'm going to go through it fairly quickly without going right over your head. What's our objective here? Well, our objective is to maximize our total net present value. So our objective is total NPV there at the bottom. So I'm just going to click that cell, and it puts D20 in that set objective field, and we're ready to continue. Now we want to maximize that, so we'll leave max checked. Now, by changing what cells, we want Excel to find values in which cells. Well, we wanted to find values in the build warehouse and build factory, those two cell regions. So the build warehouse region is those two blue cells there. Now we also want the build factory, so we're going to put comma and then highlight the build factory. And see, it puts those two cell regions in our by changing variable cells. Now the thing is, I have named all those cell regions with the define name feature, but you don't have to use those. You can actually select the cell regions you want. So that's what I'm going to do in this video because I've done it the other way in all my other ones. Now we do have several constraints in this problem. Let's go ahead and add our first constraint. Remember I said this is a binary problem. So we're either going to have 1 or 0 in our solution down in the blue regions. So we got to tell Excel that constraint. So we got to say, hey Excel, whatever you put in build warehouse or build factory has to either be a 1 or a 0. And the way we do that is we go ahead and select our first region, so build warehouse. And in the middle drop down box you will see an option that says BIN, and that means binary. So we're telling Excel that whatever it finds for those two cells has to be either a 0 or a 1. So it equals binary. So we'll click OK. Now look at this solver parameter. Now where it says set objective, it says total NPV. And where it says by changing variable cells, it says build warehouse, build factory. Now remember, I just selected the cell regions right in Excel. But when we come back into the solver, it actually uses the names we defined for those regions. So you can see it's 6 inches one way, half foot the other. It does the same thing. So we have several other constraints. Now if build warehouse is binary, build factory has to be. So we'll go ahead and click add. And we need build factory. Those two blue cells must also be binary. Click OK. Again, if you look, it says build factory has to be binary and build warehouse has to be binary. Okay, so what other constraints do we have? Well, we know that our capital spent, which is our purple cell under capital spent, must be less than or equal to our capital available, which is $10 million. So easy enough. I just select the cell reference for each one, and then the solver adds it in there. So we'll go ahead and click OK. And we come back and it says capital spent must be less than or equal to capital available. Fantastic. Now we have another constraint below that, and that is total warehouses must be less than or equal to maximum warehouses, because we can only have a maximum of 1. So we'll go ahead and click add constraint. So total warehouses must be less than or equal to the constraint under maximum warehouses. Go ahead and click OK. So we have build factory has to be binary. We have build warehouse has to be binary. Capital spent has to be less than or equal to capital available. And then our total number of warehouses has to be less than or equal to our maximum allowable number of warehouses. Now we do have one more. Can you point it out? Well, if you notice in our blue region there at the bottom, we do have some less than or equal to signs. So what does that mean? Well, remember that we can only have a warehouse if we have a factory. So we're never going to have a situation where factory is 0 and warehouse is 1, because that means there's a warehouse without a factory. So another way of saying that is that build warehouse must be less than or equal to build factory. Let me say that again. Build warehouse must be less than or equal to build factory. That will keep us from having a warehouse, which is 1, and a factory, which is 0. Let's go ahead and click add. So build warehouse must be less than or equal to the constraint of build factory. Go ahead and click OK. And there we are. So again, that just keeps us from having a 0 for factory and a 1 for warehouse, because we cannot have that. So we're just about done. Double check to make sure unconstrained variables non-negative is checked, because we're not going to be building negative warehouses or factories. Our solving method will be simplex LP, so make sure that is selected in that drop-down box. And then we'll go ahead and click solve and see what we get. Okay, it says solver found a solution. All constraints have been met. Do we want to keep the solver solution? Yes, we do. Go ahead and click OK. All right, so what do we have here? Let's take a look. Under capital spent, it appears that we have used $9 million of our $10 million. So we actually have $1 million left over. Now let's go down to total warehouses. Whoop, that says 0. So what does this mean? Well, our optimal solution doesn't have any warehouses in it. So we have 0 warehouses. So what are we going to do? If we look down at build warehouse or build factory, we have zeros for build warehouse, which should make sense because we have total warehouses of 0. And then for factory, we have a 1 and a 1. So in practical terms, what does this mean? Well, this means that in order to maximize our net present value, which is the red cell there at the bottom, in order to maximize that NPV, we're going to build 1 factory in LA and 1 factory in San Francisco. And that will give us a maximized total NPV of $13 million. Now, I do want to show you one more thing before we end. But unfortunately, you will not be able to follow along with me. You'll just have to sort of watch as I do it. And that's because it involves using an Excel add-in that is part of a textbook package that I use for these problems. And I'm not sure if I have the rights to distribute that add-in without written permission. So I'm going to go ahead and err on the safe side and not post it on my blog for you to download. So what we're going to do here is sort of an extended what-if analysis. What I mean by that is that if you remember in our original problem, we only had $10 million of capital available, which generated a maximized net present value of $13 million. Now, what if we wanted to know what would happen if we had different capital thresholds available? So what if we were able to raise that to $12 million? Would our net present value, if it increased, would it justify that extra $2 million? So maybe with a $2 million increase in our capital available, we could generate, I don't know, $5 million more dollars in NPV. Maybe it would be worth it to see if we can scrounge up that extra $2 million. So we're going to run different capital available amounts through the solver using an automated add-in to see what happens. Now down below, you will see this other region of cells, and if you've been wondering, that's what this is for. And on the left-hand side, we have capital available in millions, $5 million all the way up to $15 million. And our add-in is going to be inserting those figures into the solver and running it over, and then doing the next one, running it over, and so forth. But again, it's automated. It only takes a second to do. Now it will populate our warehouse, factory cells with zeros or ones. Again, that's our decision variable. So if there's a 1 in there, that means we're going to build that building. And then on the right-hand side, it will be the new total NPV based on what the solution is. So it's pretty awesome. It allows us to run many scenarios in under 1 second. It's fantastic. So the first thing I need to do is select the cell regions that the add-in will look for. So that is what the add-in needs to do its work, and it doesn't look like much, but the add-in is designed to look for a specific layout, and it will know exactly what to do with that region. So I'm going to go to add-ins, go to the solver table, and in this case it only needs 1 value. We got to tell it what to change each time. And remember, we're changing the capital available. So I'm going to go down to the column input cell, and that's the column input box, select the capital available cell, which is G12. I'm going to go ahead and click OK. Whoa, magic. That is awesome. So let's look at what it gave us here. Using each capital available figure, it told us what we should build in order to maximize our total NPV. So if we look at 5, 6, and 7, and 8 million, that didn't make a difference. So having more capital available in that range didn't make any difference. We built a factory in San Francisco and a warehouse in San Francisco. Our total NPV was 9 million. Now if we jump up to capital available for 9, 10, 11, for 9 and 10, right here, we have the same thing. And actually, this involves our solution we found above. So we built a factory in LA, a factory in San Francisco. Our total NPV was 13 million. Now, if we keep going, it gets a little bit more interesting. For 11 million, all the way up to 13 million capital available, our NPV jumps up to 17 million. Now think about this. This is why this is so valuable. If we are able to scrounge up one more $1 million for this project, we could increase our total NPV from 13 million all the way up to 17 million. So with $1 million more, we increased our total NPV by 4 million. That's a pretty good ratio. So through this what-if analysis, we would probably want to really consider the attempt of finding $1 million more. And of course, that would be the $11 million row. And in that case, instead of just having a factory in LA and a factory in San Francisco, we would also have a warehouse in San Francisco. So we would build one more building, and that's the warehouse in San Francisco. With that $11 million of capital, we could produce $17 million in total NPV. All right, so let's go ahead and stop there. Again, thank you so much for watching, and I look forward to seeing you next time.